everyone, welcome back to the Science Behind Papers channel. Here are Sydney and Ella. In today's video, we are going to explore solar energy, how it operates, its applications, and why it is a crucial part of our renewable energy future. We will summarize the key points from a National Geographic article and analyze the science behind solar technologies. Part 1. Summary of the article. The structure of the paper includes the origin of solar energy, natural development, the utilization of solar energy, especially in the embodiment of architecture, as well as the close relationship between solar power and human beings. The sun generates energy through nuclear fusion, pp chain reaction in stars that are about the size of sun, and CNO cycle in other larger ones, emitting electromagnetic radiation, EMR. In nature, the infrared, visible light, and ultraviolet light reaching Earth are involved in the process that warm the planet and make life possible, the greenhouse effect. Moreover, photosynthesis provides food, directly or indirectly, for nearly all life on Earth, enabling the food chain to develop from producers to consumers and decomposers. Additionally, under the influence of solar energy, plant remains turn into fossil fuel upon which human beings rely for survival. Talking about harnessing solar energy. Photovoltaics is a form of active solar energy. Discovered in 1839 by Edmund Becquerel, PV cells use semiconductors, silicon, to convert sunlight directly into electricity via the photoelectric effect. For example, the International Space Station has two solar array wings, each using about 33,000 solar cells, which are able to supply all electricity to ISS, facilitating the operation and experiments in the station. Another type of active solar energy is concentrated solar power, CSP. It uses mirror, for example, the heliostats in solar towers, to focus sunlight, heating fluids to drive turbines. The largest solar energy generating system, SEGS, in California, produces more than 650 gigawatt-hours annually. Although solar energy has many advantages and convenience, we still have a long way to go in terms of promotion and large-scale application. For advantages, it is renewable, as sunlight will last in the following 5 billion years, able to satisfy the electricity need of everyone. Also, it is clean, as it requires no field work. That is to say, no greenhouse gases or toxic materials will be emitted after installation. In addition, solar energy is necessary to complement other renewable sources of energy, such as wind or hydroelectric energy. However, the main deterrent is a high upfront cost. For example, rooftop PV installation can exceed $20,000, which is too costly for normal families. Besides, the solar technology, whether active or passive, depends on climate and cloud cover, which are basically uncontrollable factors. Now let's proceed to part 2, article analysis and in-depth understanding. We are facing energy issues. It is estimated that by 2040, the world's energy consumption will have increased by almost 50%. The burning of coal, oil, and gas have been linked to the rising level of greenhouse gases in the Earth's atmosphere and is a leading contributor to climate change. There can be no doubt that how to implement a shift to getting our energy from renewable sources is one of the grand challenges facing the planet today. The renewable energy ultimately originates from solar power. I'll explain how solar panels work by focusing on the remarkable semiconductor properties of silicon, the key material that makes photovoltaic energy conversion possible. Let's start with silicon's atomic structure. Pure silicon has 4 valence electrons that form strong covalent bonds in a crystalline lattice structure. This arrangement creates 2 important energy bands, the valence band where electrons are bound, and the conduction band where electrons can move freely. But pure silicon isn't enough. To make it useful for solar cells, we intentionally add impurities through a process called doping. When we dope silicon with phosphorus atoms, We create N-type silicon with extra free electrons. Conversely, doping with boron atoms that have 3 valence electrons creates P-type silicon with positively charged holes where electrons are missing. The magic happens when we combine these materials to form a P and N junction. When sunlight hits the solar panel, photons with energy greater than silicon's bandgap get absorbed. The electric field at the P-N junction then sweeps these electrons towards the N side and holes towards the P side. When we connect an external circuit, the electrons flow through it, generating usable electricity. However, the process isn't perfectly efficient due to several loss mechanisms. Commercial silicon solar panels typically achieve 15 to 22% efficiency due to limitations like thermal losses and reflection losses. In summary, silicon's semiconductor properties, its band gap structure, doping characteristic, and P and N junction behavior form the foundation of modern solar panel technology. While not perfect, this remarkable material has enabled the solar revolution we are seeing today. Now we are coming to the end of the show. Solar energy is undeniably vital for a sustainable future. While challenges like cost and storage persist, innovations in materials and design are accelerating adoption. As the article notes, sunlight delivers more energy in 1 hour than humanity uses in a year. Our task is to harness it efficiently. Thank you. Here are science behind papers. We welcome your questions.